All right. So I've been wanting to make a video about the solid principles, the design principles that enable us to build agile, evolvable code. But I realized before I did that, I wanted to talk a little bit about interfaces. Specifically, I wanted to talk about required interfaces and provided interfaces. So throw a little title on here. Boom, there's a title for y'all. Okay, so before we can talk about that, well, you might have heard of required and provided interfaces from the point of view of UML diagrams, specifically from component diagrams. In a component diagram, the socket is the required interface, and the ball or lollipop, that's the provided interface. But before we get into all that, I wanted to really just talk about what the heck is an interface. So let's create a dog groomer. We just sent our dog off to get groomed and came back with a nice haircut and trimmed toenails. So here I'm going to use UML and talk about defining interfaces with a class diagram. So what I've done here is I've defined this nice little class called a dog groomer. And a dog groomer does a few things. This dog groomer can clean your dog, it can trim your dog's toenails, and it also does a little internal business to notify a customer. So this being a class diagram, the plus sign means that this is a public method, and a minus sign means it's a private method. So when we create an interface, we are really talking about the publicly available methods. The private stuff stays private, and when you implement an interface, it doesn't really care about the private stuff because every class that realizes an interface might implement the private stuff differently. We write our unit tests off of those public methods. So what is an interface? Okay, so these are the interface. We don't have to create a separate class for a dog groomer to have an interface. It already has a provided interface. It's public method clean dog and a public method trim dog's nails. So any class that calls this can access dog groomer functionality through this interface. What makes that a little confusing is that in C# and Java, we create classes called interfaces. So let's go ahead and create an interface for dog groomer. All right, so we have extracted an interface from the dog groomer class and created a provided interface called iDogGroomer. Sometimes your interfaces are end with an able, like this is iDogGroomer able. But for the most part, the interface represents the provided interface of the class from which it was extracted. You'll notice that this interface doesn't have any private or internal methods with it, because if you were to have another class implement this same provided interface, it would only really be able to implement these public methods. So this is a provided interface. Now, the thing about provided interfaces is that if I were to call this interface, let's say a customer wants to groom their dog, and they could call the provided iDogGroomer interface. The customer is kind of unstable, and the reason they're unstable is if this interface that is a provided interface of dog groomer changes, the customer will require code changes. So we might, for example, change our mind and we want to rename this method from trim dog's nails to just simply trim nails. Well, that will require us to change the name of this provided interface, trim nails, which would then incur a change to the customer class. So imagine if you had all sorts of classes that were consuming this interface. And those arrows, by the way, should be open-ended because it's a dependency arrow. This is a realization arrow. So you could have a customer and a shop, and a zoo, and they all need groomers. So if we change this interface, well, we've now incurred a code change cost to all of these clients. So what if let's take our zoo sample here. What if we didn't want to break zoo? What if we wanted zoo to define what it means to groom dogs? In fact, what if zoos needed to groom more than just dogs? Now, what we've got here is we've got a required interface that's different than the provided interface that was provided by dog groomers. Instead, we have an interface that was defined by zoo because zoo said, I need animal groomers. And I don't care who's going to groom my animals. I just need you to do these things. I need you to clean an animal and I need you to trim the nails. I didn't ask you to clean dog and I didn't ask you to trim dog nails. I asked you to clean animal and trim nails. Zoo is making the rules. Zoo is the one hiring an animal groomer, so zoo gets to make those rules. So this is a required interface. Now, the thing about a required interface is that makes zoo really stable, but inversely, if a dog groomer realizes that interface, notice that I have to change the dog's functionality. So what I've done here is for dog groomer to successfully realize animal groomer, I've now incurred a code change cost to dog groomer. We could have any number of classes realize that groomer interface. So if zoo has a business requirement change that says, we're not just going to clean animals, we're going to clean creatures. Well, now I have to make a code change to all of the code that realizes this interface. So what we've done is we've incurred a trade-off. So over here, we said that when an interface is provided, the class that realizes it is stable. The classes that call it, well, they're unstable because if there's ever a change to the interface, then we have to do code changes for those calling classes. And that would require testing and integration testing and regression testing and all that good stuff, very expensive. Over here, we said the opposite. We said, well, zoo, it can't change. It gets to define the rules. So it created a required interface. And all these folks who are now desperate for work, they're willing to change their interface to meet the needs of the zoo. So in both cases, there are things that are stable and there's things that are unstable. And we as architects or developers, we're making decisions about whether we want to create stability one way or the other. So now a really interesting thing happened here. If you're familiar with the solid principles, you might be familiar with one of those called dependency inversion. And that's kind of what happened here. Sort of draw that out. So here I've drawn a little boundary of dependency. So on this side of the fence, we've got a zoo, and that zoo depends on this provided interface. This provided interface realizes this dog groomer class. So zoo is dependent on the dog groomer. But what if zoo is the most important thing in the world? We have this very complicated zoo system with a lot of requirements. And dog groomer, well, they're a small shop, or maybe it's just one individual who comes in, they're a dog groomer. The cost of changing the dog groomer is a lot cheaper than the cost of changing zoo. So we don't want zoo to incur that cost. We would love to be able to invert the dependency. Is there any way that we can move this boundary down? Now, when I move the boundary down, look what happens to those arrows. That that arrow was pointing down. Now I move the boundary here, and now the arrow is pointing up. That's a dependency arrow. Even though it's a realization arrow, it means the dog groomer is dependent on this interface. It must realize this interface. So by moving this boundary, we've inverted the dependency. So here the zoo says, well, let's move this back up. Zoo says, well, actually, I depend on an animal groomer. And I'm going to tell you what it means to do animal groomer things. And along comes a dog groomer. And the dog groomer really wants the zoo's business. So they're going to come over here and they're going to promise to realize this interface. And as we said before, we now clean dog needs to become clean animal. Trim nails can stay the same. And it can still notify customers, but zoo really doesn't care. It's not part of the interface. So what we've done is we've inverted the dependency by creating a new design where zoo is requiring an interface as opposed to dog groomer providing an interface. From a code point of view, not much has changed. You still have 3 files. If you're coding in C#, you have 3 .cs files. But the code that is being protected, the code that is becoming stable changes. Here, dog groomer was more stable than zoo. Zoo is more stable than dog groomer. So that's how you use required interfaces to implement dependency inversion principle. So that's one of the 5 solid principles. It's D, dependency inversion. All right, so while we're at it, let's talk about the interface segregation principle. So let's steal our example here. If we had the zookeeper, and maybe this was a zoo that was created by one fellow who did all the things. They were a super zookeeper and they had a lot of responsibilities. They would clean the animal, they would trim the nails. They don't really need to notify customers because they work for the zoo. But other than that, they also feed the animals. You can't be a zookeeper if you don't pick up the poop. So the zookeeper, you know, they started their zoo business. They were an employee 1 of 1. And so they said, to be a zookeeper, you need to do all these things. So I'm going to tell you what it means to do my job. In other words, the zookeeper is defining a provided interface. And that works great as long as the zoo, you know, isn't very busy and they don't have very many animals. So here, but there's a problem. This interface does too many things. This interface is tightly coupled. There's multiple responsibilities. A zookeeper is kind of a generic role. We could split this role. When the zookeeper gets too busy, they could hire someone else to help out. Maybe we want to split the role from like a groomer, an animal groomer, and maybe we would also like to define what it means to be, let's say, a caretaker. So we could segregate this interface. That's the interface segregation principle. We want to split this up into the smallest units of responsibility. So we would get rid of this kind of monolithic interface, get that out of there. And instead, we let the zoo define the roles. Instead of defining the roles around the one person, we're going to define it around what the zoo actually needs. Well, the zoo needs someone who can groom the animals and someone who can be an animal caretaker. Now, of course, even when you define the roles, the zookeeper's, well, still one person doing all the work. So it would look like this. This zookeeper class would realize both of these interfaces. And that's okay. The methods inside of zoo, maybe there's a method inside of zoo that says groom animals and it calls the animal groomer. But that method doesn't need to know about caretaker stuff. And then there could be another method inside a zoo that says take care of the animals. and it calls the animal caretaker. And again, it doesn't need to know about the groomer stuff. So at least the code inside of Zoo starts to look cleaner. Sure, it's a little messy. This zookeeper is doing a lot of work, and maybe we can split that up. We'll talk about that in a little bit. So one of my favorite solid principles is Liskov's substitution principle. And when Robert Martin created the solid principles, he created a handful of them, but a couple of them he took from other people. And Liskov's substitution principle came from Barbara Liskov. And the idea was you should code to an interface. Well, that's really what a required interface is. So let's kind of draw that out. We'll focus on animal groomer. So let's say we're concerned specifically about the zoo's ability to groom animals with an animal groomer. This code would still work because the zookeeper realizes this animal groomer interface. But what if the zookeeper had to retire? Well, and maybe the zoo just couldn't train anyone on campus to do that work. So they needed to be able to swap the zookeeper with third-party groomer. Now, of course, this groomer doesn't need to be able to feed the animals or pick up the poop. All it's required to do is clean the animals and trim the nails. Now, this is going to be very different code. Part of that code is going to be maybe they take the animal off campus and maybe they trim the sheep in the back of their truck or something. I don't know how groomer people work, but maybe there's a dog groomer and they take it to their shop and they, whereas the zookeeper, maybe there was a building out back and they took care of the animals there, or maybe they just took care of the animals right inside their cage. But it doesn't matter how they do it. What matters to the zoo is that you do it. And here the third-party groomer promises to realize the required interface of animal groomer. Now here's the really cool thing. Zookeeper is replaced with the third-party groomer. That's a code change. But the zoo requires 0 code changes. The zoo doesn't even know that the zookeeper didn't show up to work today and was replaced by a third-party groomer. The zoo just said, hey, it's time to clean the animals, get the animal groomer and clean the animals. And the third-party groomer is going to do it and the zoo will be fine. So Liskov's substitution principle says you should be able to swap the things and not incur any code changes or breaking changes to the calling code. So required interfaces enable you to do that. If it was a provided interface and we went back to where we had a zookeeper interface and the zoo was calling zookeeper interface, and then along comes third-party groomer with their provided interface and they do things a little bit different. Well, now the zoo's got to change how it calls the groomer. But if the zoo can get away with defining the rules of what it means to do grooming stuff, that's a required interface. Required interfaces allow us to swap our dependencies. We can. All right, so what happens if we can get away with letting the zoo define all of the interfaces? So over here we got a class. It's called zoo. And a class zoo has a dependency on, gotta make sure you use the right arrows or people are going to be confused. That's why we use UML, because we can all speak the same language. This open arrow means zoo has a dependency on animal groomer. And when you're coding to zoo, you can define any number of required interfaces. In fact, if you are using test-driven development and you're writing unit test after unit test against zoo, and you want to be code complete with zoo, you don't need to know anything about its dependencies other than the fact that you require them. And I'm trying to draw this a certain way to make a point. I want it to look like I'm caging in the zoo with all of these interfaces, acting like a little protective shield. Let's define the rest of these. All right, so you get the idea. So the zoo, they've been in business for a while and they started to realize, well, there's a lot of things involved in running a zoo. We have a lot of responsibilities. We need to hire quite a few people to get things done. So what we've done is we've defined the business of doing zoos. This zoo class, it has all of the business requirements and it knows everything that it requires. So it has defined all of its dependencies, and we were able to write unit tests and mock up every single one of them. And lo and behold, we're done. The rules of what it means to run a zoo will never change. Now, certainly the janitor will change, and maybe the groomer will change, and the customer could change, but the zoo, this is how we've run our business since 1947. We're never going to change because we figured out the secret formula to running zoos. Well, then that business logic should be protected at all costs. And the way we do that is we code to required interfaces. So this zoo is now closed for modification, but it's also open for extension. And that's the O in the solid principles. It's the open closed principles, meaning you're open for extension, but closed for modification. The idea here is that when zoo is done, you're done, and you never have to change this again. And you don't have to because it's protected by all these interfaces. Well, what does it mean to be open for extension? Well, over here, we can implement a janitor. And by the way, looks like I'm messed that up. To say that's an interface. All right, so we have this interface called iJanitor, and janitor does janitor things for the zoo, and the zoo depends on janitors to do janitor things. And the zoo got to define what it meant to be a janitor. And so along comes a janitor, says, I'm looking for a job. I want to do janitor things. And the zoo says, well, if you do things this way, if you realize my interface this way, then you're hired. And now the janitor could say, well, I like the way you're doing things, but I also have other innovations. You know, maybe I have a magic mop that just, you know, I could wave my hand and it'll go mop up the halls while I take a nap, like Mickey Mouse in that one cartoon. But the idea is that janitor gets to decide how to do janitor things. So even though zoo is closed for modification, it's open for extension. And you can say that about any one of these interfaces. Zoo never needs to know how janitor does the job as long as they do the job the way they promise to do it. This is the contract. So once again, zoo is closed for modification because it's protected by those required interfaces, but it's open for extension because anybody can come along and realize those required interfaces and do anything else. So that's the O. What about S in the solid principles? We got single responsibility principle. Let's steal this guy because so many of these principles overlap. If you do one, you almost get the others for free. So over here, what we've done is zoo has defined 2 of those interfaces. Sure, there might be 8 of them over here overall, but we're focusing on 2 of them. Well, here we got zoo. And some people could say that the zookeeper is violating the single responsibility principle. And the reason they're doing that is because, well, they're just doing too much work. We're going to burn them out. And that makes them brittle. If the animal caretaker has a code, if there's a requirement change, well, it's going to change code here, which means we now got to test this. So because this is tightly coupled, it affects more code than it should. Well, how would we fix that? Well, we would separate classes by their responsibilities. And interfaces are a really great way of identifying those responsibilities. So we could hire a caretaker to help our zookeeper friend. So now the zookeeper won't burn out. And maybe the zookeeper says, you know what? I just like grooming animals. I don't want to caretake. I don't want to do anything else. I'm going to change my title to just groomer. So we have separated the responsibility of these classes by their axis of change. The axis of change is the axis of responsibility. And how do we identify, how do we split up the responsibilities? Well, typically a class is prone to change when the requirements for a user changes. And previously we had a zookeeper class that had the requirements for 2 users, but we really have 2 users here. We have the animal groomer and the animal caretaker. So odds are really good. The requirements for the caretaker are going to change at a different cadence than the requirements for an animal groomer. So if we can split these responsibilities, then this groomer code will not require any code changes if there is a change to the requirements for the caretaker. All right, so now we've kind of run through the solid principles. What about sometimes you have a situation like this? I'm being kind of greedy with this drawing, trying to get everything on one picture here. What if the zoo required an animal groomer and the only groomer in town was this dog groomer? And the dog groomer comes along and says, hey, zoo, you're telling me I've got to clean animals and I've got to trim nails. Maybe I'm telling you, I do business my way. I clean dogs and I trim dog nails. There's a problem. We can't get this to work with this without changing code. So who's it going to be? What if zoo, we designed zoo to be closed for modification, but dog groomer and their business, they closed their business for modification. Well, how are we going to meet in the middle? Well, clearly the dog groomer can kind of do some of the animal groomer things. What we have is a communication problem. So we just got to change our language. Well, the way we do that is we use adapters. This is one of those design patterns that you should be real comfortable with. So we'll create a dog groomer adapter. And this dog groomer adapter, well, it'll go ahead and it'll realize the animal groomer interface. So here it's got the same methods defined by the required interface, but it's going to do something else. It's going to have really no code inside of it except to call this provided interface. So what you have here is this adapter's purpose in life is to do nothing more than be a translator between the 2 groups of people. You've got zoo saying, okay, I'm just going to say clean animal. You go ahead and take care of that for me. And the dog groomer's like, okay, cool. I'll be the man in the middle. I'll go, subcontract a dog groomer. And dog groomer adapter knows that when the zoo says clean animal, what they really mean is clean dog. And so they just simply pass that method on down. So that way you can have 2 stable pieces of code call each other through adapters. Now you might look at this and go, man, you've just made my architecture really complicated. In the olden days, I used to just call dog groomer directly. I didn't have to do all this stuff. And yeah, it is a little complicated, but the adapter's probably going to be 1 line of code for one thing. And you get a trade-off. You've made zoo a lot simpler because zoo now doesn't have to have a bunch of if statements to check all the different groomers. Maybe there's a cat groomer and a camel groomer and a mouse groomer and a dog groomer, and it's iterating through all its groomers saying clean animal, clean animal, clean animal. It doesn't need to think about, am I a dog, am I a cat? It's just going to clean the animal. So the zoo code just got really simple and really testable. All right. I think that covers it. I think the next video I'll do, I'm going to talk about how all of this enables us to then architect our applications using multiple components or packages, and how these required interfaces, they kind of they help us define the boundaries of a component so that we can create plugin components. And just a little sneak peek to that is in a component diagram, you might have a component called zoo. And this is where the lollipops come into play. So here you got a provided interface, and this interface might be called, we call it zoo, because it's a provided interface of the zoo. If anybody wants to use the zoo, they got to do the things the way the zoo defined it. And over here, the zoo might need to contract out a groomer. So we have the socket, and we would label that socket to do animal groomer things. And certainly along could come an animal groomer. We draw our little dependency arrow down. Dependency arrows are dotted, they're open arrow. But here we're drawing the arrow between the ball and the socket. So what we've done here is with this component diagram and using the ball and the socket, we can represent the provided interface at the boundary of the component and the required interface at the boundary of the component. You might be thinking, well, why does this plugin have a provided interface? Because if zoo defines the interface, how can it have an interface? Well, that's because the realizing class, it does have an interface. It's just realizing the required interface. So I'll get more into that next time, but I hope this has been helpful. All right.